So I'm gonna talk about Motivic Steenrod algebra and Motivic cohomology spectral sequence, but so I probably tell you what these two things are, but I want to start with purely topological example. So topological case. Oh, I also need to mention, before I started, I need to mention that this is work still in progress, so some places I will just hide from you, but anyway, I'm pretty sure about the final results, but I'm not pretty sure about some methods I use. So let me start with Attia Hirzebruch spectral sequence. So you probably know how to write it down. So it has the second term HP of x with coefficients in kq of a point, and so I mean the classical case converges to a K-theory, to topological K-theory. So x here is topological manifold, so with some good properties, and so H here is just singular cohomology, and K I mean complex K-theory, so K to K equals to Z, and K to K plus 1 equals to 0. So in some sense, this spectral sequence just splits in, just has a half of zero rows. So it can be just squeezed. We can just forget about these 0 rows, and it has some more compact form. So we can rewrite it. We can actually forget about this term and write Z here, just re-index it. So we can write the spectral sequence which starts in cohomology of X and converges to K-theory of X.
Write down the second term of this new spectral sequences.
Okay, it's HP XZ. That's one row. The next row HPXZ, and so on. So all the rows are just the same. But of course, spectral sequence is quite a good tool to compute something, but it's not sufficient just to know its E2 term. We also should know something about differentials. Of course, differentials just make all the machine running. So what we do know about differentials, it's some facts about differentials. The first, probably almost obvious statement, if we consider this spectral sequence with Q coefficients, with rational coefficients, so it degenerates when E2 equals to E infinity. So K-theory rationally splits. K-theory rationally can be computed in terms of cohomology without any differentials. And the second thing I want to say, with Z coefficients, if we consider it with Z coefficients, it becomes too tangled. So you cannot say much about this spectral sequence with Z coefficients because it has so many differentials, and it has, and all these differentials just reflect effects for different prime numbers. So, and they interact with each other, so you get something messy. So it makes sense to restrict ourselves to some quite big but very simple coefficient ring. I think we should consider p-local numbers. P-local numbers, so they are rational numbers such that n is mutually prime to p. So the first investigation of differentials of this spectral sequence was made by Victor Buchstaber. It's quite a long time ago. It's 1969. It was a sequel of papers, probably up to 1972 or 3, something like that. He investigated actually not p-local coefficients, but p-adic coefficients, but not there is no too much difference between them. So he used some strategy of the proof, which I, in some sense, inherited from his research. I will also use the same philosophy, but of course, all the approaches will be completely different in case of Motivic cohomology. So in topological category, everything is so simple. You can apply spectral sequences. You can do a lot of filtration, skeletal filtration, and so on. But in case of Motivic K1 category, so things are much more different. Okay, but anyway, the philosophy is still similar. So let's now pass to the algebraic case.
Explain what is the first differential non-trivial in this singular, I mean, in the topological situation?
So I will give the same, that's actually the same answer for two cases. So I will give it a little bit later, and it will serve both as a differential for algebraic and topological cases. Do we have... yeah. Thank you. Okay, let me pass to the algebraic case. So in the algebraic case, we consider some algebra geometrical counterpart of this Atiyah-Hirzebruch spectral sequence. So we take we want to have a spectral sequence which starts from some cohomology of algebraic variety, and that converges to algebraic K-theory of this variety. So G is maybe algebraic variety, or in the best case, scheme, or in maybe a fine algebraic variety. But in the simplest case, it's just a spec of a field. So even in case of a spec of a field, this is quite non-trivial result. So first of all, the existence of a similar spectral sequence was assumed by Beilinson in his list of hypotheses, and the first actual approach to construct it was done by Bloch and Lichtenbaum. So they considered the case of spec of a field and used some methods to interpret Motivic cohomology as generalized Chow groups, but this approach was actually never completed and never published. So there exists a preprint with some gaps in the proof, and the authors just tells it was never, it would be never completed. So it was the first approach. And the second, first successful, was a paper of Friedlander Suslin. It's 2000. So they considered the case of algebraic, of smooth algebraic varieties, and they constructed this spectral sequence. So I will write the exact form of this spectral sequence just a bit later. So I should here mention two more people who make some work concerning the spectral sequence. So this is Vladimir Voevodsky. So what we have in topological case? In topological case, we can how can we construct this spectral sequence? So the most natural way we can just make some filtration on X. Of course, alternative way we can try to filter the spectrum K. And Voevodsky was a person who just explained that we can try to filter just to slice the spectrum which computes algebraic K theory in such a way that every slice will be Eilenberg-MacLane spectrum, shifted Eilenberg-MacLane spectrum. It was actually a different approach from Friedlander-Suslin, and very different approach was Dan Grayson, who just found very nice approach, but that's a little bit aside from the mainstream.
Sorry, did Friedlander-Suslin rely on Bloch-Lichtenbaum in the beginning? No?
Excuse me?
I believed that the first paper of Friedlander and Suslin on this subject it was a globalization of Bloch-Lichtenbaum. No?
No. So it's, in some sense, it's a globalization, but the result of Bloch-Lichtenbaum was never completed. So there was nothing to globalize, actually. They used some ideas of Bloch-Lichtenbaum and some approaches of them, but not. Yeah, but not them. Okay, and so let me now finally write the formulation of. So I will call it Motivic cohomology spectral sequence, and let X be a smooth algebraic variety over K. Then there exists naturally defined spectral sequence such that at E2ij is hi minus j of x comma z minus j, and this converges to k minus I minus j of s. So if you're not familiar with, so here H is Motivic cohomology, so Z is the Motivic complex of Voevodsky, and K is, of course, now algebraic K theory. So if you're not familiar with Voevodsky technique and with A1 homotopic theory, you can just think of it as a usual topological case, actually, but assume that you're not permitted to do some things. You're not permitted to apply some technique. So I will tell exactly what you're not permitted to apply, but so it's some sort of a game. So and this spectral sequence encapsulates a lot of very useful algebraic invariants. I will just write and just a moment, and it's important for us the differential dn. It goes from En ij to En I plus n j minus n plus 1.
HPQ это то же самое, что HP от x к степени в задатку.
Yes. Yeah. So here it's not right indexation. So here I don't have right indexation. So maybe I should write stars here instead of PQ. Okay, so let me write some part of E2 term of this spectral sequence. So it has some very interesting form. So it starts from z, h naught of x z naught. Then we have the next row. So since the complex Z1 has cohomology in two places, and we have O star and Picard group, and here we have, so next we have zero question. I will tell you what the question mark is. Here we have K32, K22. Here we have something. Here we have Chao 2, and so on. So here we have K3, 3. Here we have Chao 3. And so this spectral sequence can be, here we can consider several regions. So the first region, I will call it Beilinson region. So it's hypothetically zero. So from Beilinson conjecture, it should follow this, in this region we have zeros. So under some conditions which I don't want to mention. So the second important region, so I call it Milner region. So this region, assuming that X is a spectrum of a field, this region gives us exactly Milner K-theory of a field. So this is H, N, N. So this is a Chao region, Chao diagonal. And I should also mention that this triangle, in some sense, reflects geometry. So it makes some sense to consider this region when you're interested in geometry. And this region, in some sense, arithmetic region. So if you consider spectrum of a field, you have nothing here on the right. You have everything concentrated here, and here we have Milner part. So you can see that a lot of algebraic things are encapsulated here, a lot of important invariants. So of course, the next question is whether we can restrict to consider only E2 term, or we should do something different. We should go further and try to compute differentials. So let's restrict ourselves to P local coefficients. So I should also mention one fact due to Levin, that with Q coefficients, everything splits. So it's quite expected, of course. Yes, and I will always assume that P is greater than 2 here. So the case P equals to 2 also can be considered, but it's a little bit different. So how we already got an explanation yesterday. So 2 is a very different prime number. Yeah.
Question. Can you write down how the second differential works? Means from just from one point to another point, just to indicate this.
Just one shift here and two shift here. Pardon me?
Point в шахматах.
Yes. Yes, like Springer. Okay, so now let me explain how we can, what we can say about these differentials, and formulate the following theorem. So in Motivic cohomology spectral sequence, for p greater than 2 and p local coefficients, the following statements hold. First of all, dn equals to 0, provided that p minus 1 doesn't divide n minus 1. The second statement, the first non-trivial differential is dp, and it equals to some alpha times b times p1 times r small. So let me...
Sorry, could I ask you a stupid question? Where are the axes in your picture? I think that the line bounded the Berlin region should be vertical, actually.
What?
Ну, что такое регион Беллинсона? Когда J там меньше подкрутка меньше нуля. Кремль она не
подкрутки, а когомологии.
Когда отрицательный номер когомологии.
Что?
Когда отрицательный номер когомологии. Отрицательный номер подкрутки — это вообще как бы там комплекса просто нет, если у вас J меньше нуля. А вот если у вас йод меньше нуля, если у вас когомология меньше нуля, там как раз и возникает Беллинсон эффект. So, and the first non-trivial differential has the following form. So let me just tell what all these letters are. So R is just coefficient reduction. So we can go from p local coefficients to z over p coefficients. P1 is the first Steenrod power operation. So it was constructed by Voevodsky, and it goes from z over p cohomology to z over p cohomology shifted. B fractured is Bochstein. Bochstein corresponding to the following short exact sequence: z over z p local, z p local, z over p 0. Here we have multiplication by p, and finally alpha is just some z over p. Is just some invertible constant. Invertible in p local. In z over p.
Еще один момент. So there is a very first diagonal. Z, X.
Yes.
So is it true that this diagonal, how to say, reflects
K naught. Yes. Yes. Oh, probably I should say. So if we go along these diagonals, we get here something corresponds to K naught. Here something corresponds to K1, and so on. And just let me.
So we have composition. DP is a composition or something?
Yes, it's a composition. So we first, maybe I just make one mistake. So I should have B here and alpha here, and alpha is a z over p constant. So thanks for your correction. So it's a composition. The first, so we want to get differential. What we have to do, we first restrict to z over p coefficients. Then we take Steenrod power. Then we multiply by some constant. And then we take Bochstein.
My question.
Yeah, sure.
Is it true that the first Steenrod power is also the Bochstein operation?
No, it's not true. Bochstein has degree 1, 0, but the first Steenrod power with z over p coefficients has degree 2p minus 2, p minus 1. B degree. No. In case of z over 2 in usual topology, if you consider z over 2 coefficients, certainly Bach-Stein coincides with the first Steenrod. But if you take odd primes, it's already not true in topology. But moreover, it's not true in algebraic geometry. Okay, let me just explain the philosophy of the proof, and then, if I have time, I will tell something about.
Is it true that when you take complex numbers as your variety, okay, when this spectral sequence induces this one, when does the algebraic spectral sequence is the same thing as the topological one?
I think never, actually.
They converge, say, to one.
We converge to different things, first of all.
Yes, but you can sort of say take projective spaces of complex numbers.
No, they do not coincide as well.
Of course, you can find some trivial cases where they probably coincide, but it's not interesting. Okay, so strategy for proof. So unfortunately, the proof that I have up to date is not effective. So it makes me a bit sorry. But let me also make one remark. So here we have some nasty constant alpha, which is non-zero, which is z over p constant, and you can ask me, oh, it's so ugly to have some undefined constant, but I think no one should care about this alpha because it's z over p invertible, and it actually defines the same, independently of alpha, we got the same terms of a spectral sequence since it's invertible, so everything is defined up to some automorphism of terms of spectral sequence, so no one actually cares. Okay, so what about the strategy? So first of all, I'm gonna show that dn equals to 0 for p minus 1 not dividing n minus 1. It's quite simple part. And another thing I got as a bonus, so that dp can be queued after multiplication by p. The second step, assume that dn equals to 0, that all dn equal to 0 for n smaller than p. Assume we already know the first. Then dp is a bistable cohomological operation. So here I mean cohomological operations, Motivic cohomological operations, which were introduced by Voevodsky. And since in Voevodsky category we have two different suspension isomorphisms, we should take care not only of one suspension, we should take care of two suspensions. But actually, Voevodsky gives us some relax, and we should actually take care only of one suspension. That's the T suspension. So I can write here, it's a T stable. The third stage, we should compute Steenrod algebra with p local coefficients. So since our differential dp is now, assume we now know that this is a stable cohomological operation, so it should be an element of the Steenrod algebra, of the corresponding Steenrod algebra. We actually interested only in one term of the Steenrod algebra corresponding to the degree of our differential. And since it's of order p, we're actually interested in p torsion, only in p torsion in the Steenrod algebra. So we want to compute this thing, and it happens, so we are lucky, it happens to be pretty small. It's only z over p. And now,
No restrictions to the base field here.
where is restriction to a base field?
No restrictions.
No okay. About restriction to a base field, I'll tell you later. So it's only z to the p. And we are just one step off our aim. Finally, we already know almost everything, but up to this constant. We are not sure whether this constant is 0 or not. So the last step, we should show that dp is not 0. And of course, the best way to show it, we can just make an example. We can just construct a very, very explicit example for which dp is non-zero. Of course, then, if we have just one case where dp is non-zero, then it's not 0 as an operation. Okay, now let me tell some things about the proof itself. So I will start from the first step.
Could I ask you, will this statement remain here at the end of the talk?
I will try.
Okay.
I will do my best.
Okay.
So assume that we have some integer which is invertible in ZP, in P local. Then there exists a result of Levin again. So we can construct Adams operations. We can construct Adams operation psi k, which is of course an operation in K theory, but it also has a representation on the spectral sequence. So it acts on all terms of spectral sequence, and it acts in a very tame way. So actually, if we take alpha to be some element in Motivic cohomology, so this is an element in E2 term. So we are only currently interested in E2 term. Then psi k of alpha is nothing more than k power minus q alpha. So it divides alpha by the qth power of k.
I'm sorry, we take Motivic cohomology with what coefficients?
P local coefficients. And k is invertible.
Just P local, not torsion.
Just P local.
Okay. And your alpha on the right blackboard is not the same as on the left blackboard.
What do you mean?
Alpha here is a cohomology element, and alpha on the left.
Oh, it was very, okay. It was very old alpha. It's already renamed. Let it be gamma. Okay, thank you. So then it's just multiplication by k power minus q. And we also know that Adams operations compute with differentials. It's also known from Levin's result. So dn psi k equals to psi k dn. So operation psi k is an operation of degree 0, 0 in some sense. It acts from Motivic cohomology to itself. So what we can exclude from here, we know how psi k acts on gamma. So we can write that k power n minus 1 kills dn. So we just subtract one part from another and use this relation. So we got this. So dn dies after multiplication by some integer number. So as the first corollary here, we got that with rational coefficients, this spectral sequence degenerates at E2 term. But we need something more. Let me make one definition. I define the constant m of I as the greatest common divisor of the following expressions. I take k power n capital times k power I minus 1, where k runs over all positive integers greater than 1, and I assume that n is much bigger than I, so it actually doesn't make sense to specify, so it's independent on n capital. So one can check that these constants are well defined, and I call them Kerver-Milner Adams. Just a moment.
Yes, it's okay.
Constants. Yeah.
It's okay.
So the funny remark that these constants have some number theoretical meaning, and they are quite closely related to denominators of Bernoulli numbers. But we are not actually interested in Bernoulli numbers. We're interested in different matters. So I just give you the result how to compute these constants. It's not so difficult, but this computation has a name. So probably the first who computed them was Frank Adams. So just a lemma due to Adams. So denote by nu p of n the greatest dividing p exponent of n. So what I mean? I mean if we take some n, then n equals to 2 power u2 of n times 3 tau nu 3 of n times so on. So it's easy definition. Then nu p of m of I equals to 1 plus nu p of I for I congruent to 0 modulo p minus 1 and equals to 0 in all other cases. That's true for p greater than 2. And actually, I'm not interested in the case p equals to 2, but just for completeness, I give you the result for nu2 of mi. This is 2 plus nu2 of I for even I, and this is 1 for I odd. So from this lemma and from this statement, we actually can vary the number k, since this is a most arbitrary number with some very, very little restriction. So we can get the following corollary. What can I erase? Okay. So we can get the following corollary. First of all, assume that p minus 1 doesn't divide n minus 1. Therefore, dn equals to 0. So it's easy if we just substitute n for I. Here we got that our mi is not divisible by p, so it's invertible in p local numbers. So therefore we multiply differential by invertible number, we got 0, so therefore the differential itself is 0. And the second easy corollary, p dp equals to 0. So now we should substitute p as I, and we got our result. Okay, so we completed the first part of our proof. Let me now erase this and say something about the second part. So part 2, dp is a stable operation. First of all, I should recall what Voevodsky mean of operations. So Voevodsky defines operations on the category, or operations as an operation acting on the category of smooth varieties. So it's sufficient to check that for all smooth varieties, we have natural homomorphism. We have some functor dp, which commutes with two suspensions in the sense of Voevodsky. So there are some technical differences here, but I don't want to go into them. First of all, I should mention that dp is functorial, of course, due to the definition of the spectral sequence. So dp is a functor, and dp is defined on the category of all smooth varieties. So it's already an operation. We just should check the stability of dp. To check the stability of dp, it's sufficient to check that our differential dp commutes with t suspension. So we should take t suspension. So t is a tate object. This is a1 factor a1 minus 0. And we should check that dp of this coincide with so here it's not quite correct. Okay, coincide. So when we apply dp to t smash x, we got nothing more than suspension isomorphism of x. Certainly, t smash x is no longer smooth variety. It's some sort of a space. But we can just overpass this problem. So t smash x is homotopically equivalent to p1 smash x. So here, instead of t, we already have algebraic variety. And here we have smash product, so it's again not quite algebraic variety, but it's not hard to get rid of this problem. So we can almost write here times x.
So this is a retract, yes?
Yeah. Yes. So the last step we need to do. How does the cohomology of this thing look? It's just two copies of cohomology of x, just shifted by one with respect to another. So the shift happens due to cohomology element in P1. So in P1 we have two generators, 1 and sigma. one of a cohomology of a point. One is of degree 0, 0, and sigma is of degree 2, 1. And so what we should check now? We should now check that dp of sigma smash sigma cup x equals to sigma cup dp of x. Oops, sorry, x small. Okay, so here we have a product, and our Motivic spectral sequence satisfies Leibniz rule. So we can write here dp sigma cup x plus sigma cup dp of x. And one can easily see that dp of sigma is 0, because sigma is of degree 2, 1, and when we apply any differential, we go out of our spectral sequence. So I don't want to show, but that's of course true. So now we showed that dp is a stable operation. Okay, part 2 is completed. But I still have time. And I want to say something about 2 other parts. I have 15 minutes.
15?
Yes, I'm sure. Yes. So part 3. I will start from one example. Due to Voevodsky. And this example is nothing more than computation of Steenrod algebra with z over p coefficients. I am interested only in weight p minus 1. So I will probably omit it in the sequel. So what we have here, we have z over p for star equals to 2p minus 2, z over p plus z over p for star equals to 2p minus 1, and again z over p for star equals to 2p, and 0 in all other cases. So I also want to mention generators, canonical generators in all these 3 cases. So here, the canonical generator is nothing more than our Steenrod power. Here we should have 2 generators. One is beta p1, and the second one is p1 beta. So beta is Bochstein. That's the standard Bochstein homomorphism corresponding to z over p square, z over p. And in the last case, we already we again have one generator. This is b p1 beta, beta p1 beta. That's a composite of 3 operations. So that's the computation of Steenrod algebra. And unfortunately, Voevodsky has some restrictions on the base field. So from now on, we should assume that K has characteristic 0, and probably K is perfect. Pardon? Yes, of course. Sorry. But it was true. Okay, we should assume that characteristic K is 0. Yes, so all other technique actually works in case of arbitrary fields. But since we using Voevodsky computation, we should assume that our field has characteristic 0. So then, here I just want to hide from you some part of my computations and my arguments. I just show you the final result. The final result is the following. So we have, just a moment. we have operations from p local coefficients to p local coefficients. And we take p torsion here. When all these operations look like this, so here we have P1 B capital, so in degree 2p minus 1. I'm sorry, it's not quite true. I consider not the Steenrod algebra. I consider now operations from p local to finite coefficients. So it's some sort of Steenrod module. So we can first take Bochstein homomorphism corresponding to this to the erased short exact sequence. So here we have B capital to be the corresponding Bochstein. Yeah.
По-моему, в четвертом пункте спрятана красивая геометрия.
Да, но я только результат могу привести, я не могу привести вычисления. Okay, since I don't have much time, I just give the final result. So the final result you already actually seen. So this is z over p, and the canonical generator, which comes from this computation, actually, we should first take the reduction from p local coefficients to finite coefficients. Then we should take Steenrod power, and then we should take Bochstein. That's the canonical generator in this case. Actually, it comes from this generator. So all other generators are either in wrong degrees or die after passing to p local coefficients. So this generator dies. So we have only this generator which survives, and it just transforms to this form. Okay, so now let me just say some words about the fourth point. First of all, most of the time I worked with odd primes. But let me just make a remark concerning z over 2. So let's look at Motivic spectral sequence with z over 2 coefficients. And I assume X just to be a spectrum of rational numbers. When all this part, okay, when all this part actually dies, and let's look what happens here. Here we have K4 Milner of Q in this case. K4 Milner of Q is just z over 2 group. And it has one generator, -1, -1, -1, -1. It can be checked using Adams invariant. Then, as we go from Milner K-theory to algebraic K-theory of Q, this generator dies. So this map should be 0. But in this spectral sequence, we have here z over 2 term. So this z over 2 term should die at some stage. Therefore, there should exist non-trivial differential just going from this point. So that's exactly our differential. Of course, it's not the right case. So we consider z over 2 coefficients. With odd coefficients, we got 0 here initially. But z over 2 case just gives us some intuition and also shows that it has some beautiful relation to classical teams. And what one can say about odd coefficients? So now I will just give you the result. Unfortunately, the computation is a little bit tedious. So let's consider D to be simple central algebra of degree n and also non-split. Let's also take our variety G to be SL1D. So what is SL1D? SL1D is a form of SLn. So when we take étale cover, when we pass to some étale local neighborhoods, we got nothing more than matrices. But then you consider our we got square matrices, square n by n matrices, SL1 group SL1 locally. But when we consider the whole variety, we got some variety which is denoted SL1D, and this is called form of SLn. And one can actually check that the dimension of G is n square minus 1. Of course. So I claim that if we consider Motivic cohomology spectral sequence of a variety G with these p local coefficients, G of degree p, then the differential dp is non-trivial.
I'm sorry, what is n here?
N is p. And here is p.
So which which variety of matrices does have dimension p squared minus 1?
SLP.
Okay.
Okay, so it's not convenient to make computations exactly in this Motivic cohomology spectral sequence, so we can just change the spectral sequence. I will change this spectral sequence to Brown-Gersten Quillen spectral sequence. So there exists the natural map. So Brown-Gersten Quillen spectral sequence is a spectral sequence with this second term, just cohomology of G with coefficients in K, Q. So of course I have wrong indexation here, K minus Q. I have wrong indexation here, but I'm sorry. And it also converges to algebraic theory. And there is much more things known of this spectral sequence. In particular, there exists the following result of Andrei Suslin. If we take G to be norm variety, then this morphism gives us an isomorphism in two diagonals, in 0 diagonal and -1 diagonal. And these two diagonals are exactly what we actually need for our computation. So we can now forget about Motivic cohomology spectral sequence and think only of Brown-Gersten Quillen spectral sequence. Let me finally just write a part of the spectral sequence. May have 5 more minutes here. I can now write a part of this spectral sequence. So it looks like this. It has 0 here. It has H naught of G K1 here. It has first Chow group here. Second Chow group here. H naught of G K2. H1 of G K2. And so on. And here let me write Chow P plus 1 of G. And here, OK, here I have everything. OK, so it has a form like this. And so since we already, let's just look at two diagonals, this one and this one. Since we already know that all differentials up to P differential vanish, so we can conclude some statements. So this diagonal corresponds to K naught. And it's known that K naught of this norm variety is nothing more than Z. Moreover, this Z should be concentrated here. So our K naught, our diagonal, should come to 0, the whole diagonal, but with 0 term. And since there is no differentials going to these terms, all these terms are initially zeros. So the first potentially non-zero term is this one. Since we have the differential dp acting from here to this term. So the conclusion, if Chow P plus 1 of SL1D is non-zero, then dp is non-zero. And this happens to be non-zero. So we can just spend about 5 more pages and several hours to discuss it. And we can conclude this group is non-zero. So therefore, we got non-zero differential. And we have proven our theorem. OK, probably I stop here.